Okay, welcome to the chapter 2 video. This chapter comes to you in several parts, so we're just doing part 1 today. Chapter 2 is about functions, equations, and graphs. We will need graph paper for this chapter, but we won't need it for this first section. So if you don't have any graph paper yet, I did mention earlier during our first class, there's a resource available to you on our topics resources page, not the Blackbaud resources, but within our class, the topics page. If you go to helpful resources, you'll be able to print out some graph paper there. Okay, but we don't need that for this lesson. For this lesson, we're going to start out by talking about relations, and then we're going to talk a little bit about what domain and range are, and then we're going to pull it all together talking about functions. Now, hopefully some of this is familiar, but again, if none of this sounds familiar, what you'll want to do, and if it doesn't make sense as I'm going through it, reach out to me for office hours so that we can talk about it in more detail and make sure that we've got a strong foundation for the beginning of this chapter. So first we're going to define what is a relation. Relation, kind of like relationship, is a comparison or a way to relate or to compare different values. Okay, so there's 4 different ways in math that we can represent relations. And when we're talking about relations, it's always going to be something causing something else. So the one that does the causing is called the input. The value that we are giving as our initial value is the input, and then the value that is caused, or the effect of that initial input value, is called the output value. Okay, now you've been using functions and relations for several years now, but you might not have called them relations. So I have here a diagram of the 4 ways that we can represent relations. Our first way is ordered pairs. Now you've seen this before in Algebra 1 as well as geometry. When we're plotting on a graph, we always use ordered pairs. And the first part of our ordered pair is always our x value. X is our input. So we have a couple examples here of ordered pairs. We have the ordered pair -3, 4, the ordered pair 3, -1, the ordered pair 4, -1, and the ordered pair 4, 3. Okay, so for those ordered pairs, the first value is always the input, or the x value, and the output, or the y value, is the second value in that ordered pair. Okay, our next type of relation that we can draw out is called a mapping diagram, where we have our inputs listed and we have our outputs listed. And the arrow shows which input goes to which output. So our first input, -3, has an arrow pointing to 4. That tells me when I take -3 as my input, the result is -4. So another way to describe output is as the result. Okay, when my input is 3, my output is -1. So when my input is 3, my output is -1. And then our last number in that green box for input of our mapping diagram is 4. And so when my input is 4, I actually have 2 arrows going away from 4. And so that tells me I have 2 possible output values. That is -1 and also 3. Okay, now that's important. We had 1 input value that gave us multiple output values. That means if we look in our ordered pairs, that we have 2 ordered pairs with our x value of 4. Okay, so even though we only had 4 written in our input values once, because it has 2 arrows going away from it, that's what shows us that we use that input value twice. Our next way of representing a relation is a table of values. This is very, very similar to our ordered pairs, and we actually use tables of values to write ordered pairs a lot of times when we're solving functions. So again, it's going to be the same relation that we're showing in each of these different representations. Our x represents our input values. For an input value of -3, we can look across the table and see an output value of 4. Input value of 3 gives us an output value of -1. An input value of 4 gives us an output value of -1. And an input value of 4, notice the same input value here, gives us an output value of 3. What that looks like in our fourth representation of a relation is graphically. So on a graph, we can plot these ordered pairs. We always put our input on the x-axis and our output on the y-axis. And so our x-axis, that's the one that goes sideways. We say that is horizontal. And our horizontal axis, horizontal, is x, like the horizon. If you're looking out over the horizon, if you're watching the sunset over the horizon, it's sideways, right? Whereas our y value goes up and down, and that is vertical. Let me see if I can change that to a different color. Vertical for y. Vertical, like an elevator, goes up and down. It moves vertically. If you have sensitivity to heights, you might have vertigo. Verti means high, so vertical, up and down. Okay, let me go ahead and clear this off, and let's take a look at, within a relation, we have our domain and range. So remember we said input and output. Well, the domain is all of the input values. That word set means that we can have more than one number in our answer. So remember when we had absolute values and we could have more than one answer, we said it was a set of values. So in this case, if we take all of our possible input values, all of the numbers in our input column, or all of our x values, that gives us our domain. The same thing goes for range, except for instead of input, now we're dealing with output values. So the range is the set of all possible output values. And when we're looking at our mappings, any of the 4 mappings, we can break our domain and range, or our input and our output, into these 2 categories. Okay, so let's see if we can take a look at this relation here on the right. And the first step that I'd like us to do is rewrite this as ordered pairs. So I'm going to do 2 of them, and then I'm going to give you a chance to do the last 3. So our first point here, or our first ordered pair that we're going to create, we always start with parentheses for an ordered pair, and there's going to be a comma separating our 2 values. Our input goes first, so that's 0, and then our output, which is 10. Sorry, my page zoomed in. 10,000. Let me try writing that a little better. 10,000. Okay, sorry, if I rest my hand when I'm writing, it does strange things to the screen. So my handwriting is a little bit harder to read. So that's our first ordered pair. We took our input and our output. Then we put a comma between ordered pairs to show that they're separate. Okay, our next ordered pair, we look at our next input and output value. So that is 4, 9,744. Okay, so comma to separate, I'd like you to try making our last 3 ordered pairs. Let's go ahead and check your answers here. So our next ordered pair will be 8, 8,976, and parentheses, comma to separate points. So within the point, we have our input and our output, and then we also have commas to separate between our ordered pairs. Our next point will be 12, 7,696. And our last ordered pair is 16, 5,904. I'm going to go ahead and write my set bracket. My handwriting gets bigger and bigger across the screen. But hopefully, since I was saying the numbers as we were going along and you had a chance to work on those last 3, Hopefully that step makes sense. Going from our input and output mapping to ordered pairs. And now what we want to do is write our domain and range. So notice the ordered pairs are separate from domain and range. They are not the same thing. So here for domain, we're looking at creating a new list of numbers. So to create a list of numbers, I put that curly bracket. That means there's going to be a list of more than one answer. And I'm looking at all of my input values. So I can take that either from the input list, or I can look at all of my X values. So that's going to be 0, 4, 8, 12, and 16. Whoops. And 16. See if I can make that curlier. Okay. Notice this one doesn't have ordered pairs in it. These are just the input values. Our range, we're going to do the same thing, but for output values. So for our range, we're looking at output values. And so again, I'm going to do set bracket. That tells me I'm making a list. And I'm not going to separate my 10,000 with a comma. Normally we would put a comma after the thousands place, but before the hundreds place, or between the thousands and hundreds place. But if I were to put a comma here, that would separate values. So that would be 10, comma, 0, comma. So when we're making a list, we don't put commas to represent our place values. No comma for our place value. And then our next one, 9,744, 8,976, 7,696, and 5,904. Okay, so again, the reason we have not parentheses but curly brackets around those numbers is because they are a list of numbers. And when we're listing numbers, we put them inside of these curly brackets, which is, if you were to draw the curly brackets, it's kind of like doing an S followed by a curvy Z. And then backwards, a very curvy Z followed by an S. And those mean that we are making a list. Okay, let's take a look at our next example. I'd like you to try this on your own. Find the domain and range of this relation, and then we will go over it together. So let's start with domain. I'm going to abbreviate domain with just a capital D, D for domain. My domain is my set of all inputs. Because I'm going to be listing my input values, I'm going to put a set bracket or a curly bracket. And then I'm going to list all of my X values. So here I'm looking at the first coordinate of each of these ordered pairs. That's -3, 0, 2, 9, and 23. That's my domain. We'll do the same thing for range, R for range. For range, I'm looking at my output values. That's the Y coordinates of all of these points. And so that is 14, 7, 0, -18, -99. That is my domain and range for this list of ordered pairs. Okay. Next, we're going to look at our definition of a function. What makes something a function? Now, I had some feedback from our last video rather, that it was hard to follow along because I didn't have the definitions written out on the screen already. And so I have put the definitions on the screen. I still want you to copy these down by hand, even though these slides are still posted under the topics page. The reason I want you to copy these down by hand, these definitions, is because it's going to be much easier for you to remember them if you've written them. If you're just reading them, you've only experienced this definition in one way, which is visually reading it instead of also writing it. And so it's going to be much easier for you to understand this definition if you write it down as well. Okay, so our definition here, our definition of function is a relation. Remember, our last few examples have been about relations. So not all relations are functions, but all functions are relations. A function is a type of relation. Specifically, it's the type of relation where every or each element in the domain corresponds with exactly one element of the range, meaning that every x has only one y value. Now, if we look back at the example that we had earlier, notice this input has two output values. This x value is repeated twice. And what that looks like graphically is that I have this x value that happens 2 times. I have 2 points with the same x value. And so in order to test whether or not something is a function, I'm going to go back to that definition of function. In order to test whether a relation is a function, we can look at its graph and we can test it with the vertical line test. Meaning if I can draw a vertical line through the function, if that vertical line touches the relation twice, it is not a function. If I have something, let's say like this, where all of my vertical lines pass through my graph only one time, that is a function. Okay, so if the vertical line test means that a vertical line passes through the graph, if it passes through the graph more than one time for a single vertical line, then it is not a function. We abbreviate the vertical line test as VLT, vertical line test. So here's the formal statement. The vertical line test states that if any vertical line passes through more than one point on a graph of a relation, then the relation is not a function. So let's take a look. Try using the vertical line test for graph A. Do we think graph A is a function? Well, notice if I draw a vertical line through this graph, the y-axis is a vertical line. It passes through the graph twice. So this is not a function. A is not a function. How about B? Well, again, for B, I'm looking through here and I'm going to see if I can draw a vertical line through any 2 points. And it has to be vertical, not slanted at all. And so if I draw a vertical line through these points, none of the points overlap. None of those points overlap. So yes, this is a function. So B is a function. And then lastly, part C, do we think this one is a function? Yeah, this one, I can draw vertical lines through this function, as many vertical lines as I want. It will never pass through twice. So really what I'm looking for is, does the graph pass back over itself, right? So when I'm drawing this graph, do I ever go back over top the same graph that I just drew? If I draw this graph, I am always moving and never going back over the same path that I just drew. Always going and going and going and never going backwards. If I started going and then I curved back around, that is not a function. That's when I would fail the vertical line test. But graph C never goes back over itself. So this, yes, it is a function. So we said C is a function, B is a function, A is not a function. Okay. Let's take a look at our next slide. Here we are looking at defining functions a little bit more. So you've seen function notation before, but let's define it officially. So again, I've written out all of the definitions on screen for you instead of writing them. Hopefully that makes it easier to read. But you must write these in your own handwriting in your notes. You must write these in your own handwriting in your notes. Okay, so to define function equations, the first thing to know is, remember, the function is a relation that passes the vertical line test. So for every function, I can write a rule. And for some functions, that rule is clearer than other functions. Okay, so a function rule is an equation that represents an output value in terms of an input value. So when we talk about y equals mx plus b, that is a function rule. It's an equation that gives us the result of a function. It's an equation that gives us that relation, okay? So you can write a function rule in function notation, and what that means is our first example here, where we were given y equals 3x plus 2. This is a function, okay? But notice here we have y equals 3x plus 2. So I have two variables there. I have y and x. X is my input, y is my output. Remember our ordered pairs? X was the input, y is the output, okay? If I take that function, that equation, and I rename y, all I'm doing is I'm saying y, I'm giving you a new name, and that name is f of x. Because remember, y is the output. And so in order to get an output, we have to have an input. And so y is the output for x. That's what f of x means. It means the output for an input of x. So when we're looking at our function notation here, f of x is just another name for y. F of x is just another name for y. And the reason that we like having rules for our functions is because then we can assign input values and get output values. In other words, we can find points for our function. So if I said, let me have an input value of 1, I put 1 into my equation, the way we would say that is we would say let x equal 1. And when x equals 1, remember x is our input. So when x equals 1, we have f of 1. Everywhere that there was an x becomes a 1, and that equals 3 times 1 plus 2. And now we can find 3 times 1 is 3 plus 2 equals 5. So x was 1, f of x is 5. What's another name for f of x? Another name for f of x is y. And so we get the ordered pair 1, 5. So do you see how we took a rule? We took y equals 3x plus 2. And then we said, well, this rule is a function. So we're just going to call it f of x. And that way, if I'm given an x value, I can evaluate it, right? Just like we were doing with expressions where you substituted values into the expression, we're going to evaluate this equation to get a y value or an output value. Now, because we needed x in order to find y, x is called our independent variable. I can put any number in for x, and that number will give me a value for y. But I need x in order to find y. And so x is our independent variable, and the output that we receive, the answer that we got because we chose 1 as x, is called the dependent variable. So y, or f of x, remember f of x is also called y, represents the output of the function. And the output of the function depends on what we put into the function. So if I had put a different number into the function, I would have got a different output. And that is what makes this a function. What makes it a function is that if I put a different value of x, I would have gotten a different value for y. Let's look at an example. So for this example, we have f of x equals negative 2x plus 5, and we want to find the output for each input of negative 3, 0, and 1/4. So I made a table, and actually my table is, my input column got a little bit squished, but it should be fixed in your notes. It should look like input instead of input, okay? And we're gonna take our input values, negative 3, 0, and 1/4, and one at a time, we're gonna find our output values. So remember, our input value is x. X is our input, so we're going to replace x with negative 3. So in our function rule, we're replacing x with negative 3. That's f of negative 3 equals negative 2 times negative 3 plus 5. What is negative 2 times negative 3? That should be a positive 6. And 6 plus 5 is 11. So our output is 11. Since we had an input of negative 3 and we have an output of 11, our ordered pair is negative 3, comma, 11. Okay, let's try another one together. Let's try an input value of 0. So again, what I'm doing is I'm replacing all of my x's in my function rule with 0. I start back at my given f of x. I'm not going to use any of the information that I found for negative 3. I'm starting back at the beginning. So we have f of 0 equals negative 2. I've got another x there, so times 0 plus 5. Negative 2 times 0 is 0. Anything times 0 is 0. So then we have 0 plus 5 equals 5. If I have an input value of 0, my output value is 5. So I can write that as well as an ordered pair. Okay, our last one together, and then I'm going to give you a chance to do our second example there and try that on your own before we go over it together. So our last example together before you get to try on your own is an input value of 1/4. This one is a fraction. Don't let that scare you. Fractions work just like our other numbers. We just have a few extra rules that we have to remember. So let's see if we can remember them together. To find f of 1/4, we're going to replace x with 1/4. So negative 2 times 1/4 plus 5. Well, in order to multiply fractions, I need both numbers to be fractions. So I'm going to put my negative 2 over 1. I can always put a number over 1 without changing its value. If we have negative 2 over 1 times 1/4, multiplying, do we need a common denominator to multiply? If you think back to a couple weeks ago, we talked about how multiplying fractions, we do not need a common denominator. We multiply across. So that's the same as negative 2 times 1 divided by 1 times 4. Once we have that, we can simplify. You could have simplified before you multiplied as well, but here we have negative 2 divided by 4. They have a common factor of 2. I can simplify by 2, and so we get negative 1/2. Okay, so now I have negative 1/2, but I have to add 5. Well, in order to have fractions, we do need a common denominator. So I need to put that, right now it's over 1. I need it to be over 2. So what do I have to do to get a denominator of 2? I'm going to multiply numerator and denominator by 2. They have to be multiplied by the same number because this is not an equation, right? We can't multiply by something on both sides because there's only one side. There's only one expression here. So now we have negative 1/2 plus 10/2. Now that they have a common denominator, we can add across. Negative 1 plus 10 is 9/2. So our answer here is 9/2, giving us 1/4, comma 9/2. So notice we can do this with fractions as well. Now the example that I gave you to work out on your own, there are no fractions, but I did want to show you that it's possible to do this with fractions. And remember, you also have a calculator. You could have put that formula, the function rule, into your calculator. And if you have questions about how to do that, we can go over that in class next class, okay? So I'd like to give you a moment here to go ahead and try the next example, parts A, B, and C, and then we'll go over it together. Okay, so let's take a look at part A. If, sorry, as the instructions say, we're given f of x equals negative 4x plus 1. That is our function rule. And that is given in terms of f of x, so that's our function rule in function notation. We want to find the output for the given input. So that means we are given the input value, and the input value is x. So I want to replace x with negative 2. So that means I want to find f of negative 2 equals, I'm going to replace x with negative 2, and we always substitute in parentheses. So we have negative 4 times negative 2. If I multiply two negatives, it becomes positive, just like we saw earlier. So this becomes 8 plus 1 equals 9. This time it didn't ask for an ordered pair, just the output value. And so our answer here is 9. If you put it as an ordered pair, that's absolutely fine, but just recognize the difference. If I'm asking for the ordered pair, it has both the input and output value. If I'm asking just for the output value, that's just one number, and it's just going to be your y value or your f of x value. Okay, for part B, we're going to do the same thing. 0 is our input value, and so I need to replace x with 0. So I have f of 0 equals negative 4 times 0 plus 1. We love finding these with 0 because 0 makes numbers disappear. 0 is magical. Negative 4 times 0 is 0, plus 1 is 1. Our answer for part B should be 1. And finally, part C, we're replacing x with 5. So we have f of 5 equals negative 4. I'm going to have to erase some of my work with the fractions here. Hopefully you got that copied down. If not, you can rewind after you watch the video. Okay, negative 4 times 5 plus 1. Negative 4 times 5, and negative times a positive is a negative. So that is negative 20 plus 1. Negative 20 plus 1, be careful with this. The bigger number is negative, so my answer is going to be negative, but they have opposite signs, which means I'm looking for their difference. 20 minus 1 is 19. So our answer here is negative 19. If you put 21 or negative 21, what you're missing is that sign difference. One of them is positive and one of them is negative. So make sure you're careful on things like that. Okay. All right, let's take a look at our last slide here, writing and evaluating a function. So for this example, we're given a word problem. We're going to start by writing the function, just like we were writing expressions in our last chapter, and then we're also going to evaluate it. So our first part is to write a function. Okay, so we want to write a function about ticket price. Tickets to a concert are available online for $35 each, plus a handling fee of $2.50. The total cost is a function of the number of tickets bought. What function rule models the cost of the concert tickets? Okay, so we want to buy concert tickets. Okay, we want to know what the total cost will be, right? Cost is my output. Okay, so then what is my input? What information do I need to know before I can find my cost? Well, I need to know how many tickets I need. So my input is going to be the number of tickets. So let's call that X. Okay, So we know that our cost then is a function of X. So we can say the cost of our tickets is going to be, so how do I find the cost of the tickets? Well, they're $35 each, right? So if I buy one ticket, it's $35. If I buy two tickets, it's $70. If I buy three tickets, it's $105. So notice I'm going up by 35 each time. And for expressions, what we did is we had to multiply 35x, where X is the number of tickets. And every ticket I buy, I have to pay another $35. But then there's also this $2.50 handling fee. So 2.50, but I only have to pay that one time, right? It's $35 each plus a handling fee of $2.50. We just have to pay that once. It doesn't say we have to pay that per ticket. It doesn't say we have to pay that multiple times, just once, okay? What function rule models the cost of the tickets? There it is. Okay, there's the first part. The second part is then we want to find out, okay, so then how much will it cost for 4 tickets? And that means I want to know what will it be when my input is 4. When X equals 4, we have F of 4 equals 35 times 4 plus 250. 35 times 4 is 140 plus 250 equals 142.50. Now, what is that? What is that number? Well, that's how much those tickets cost, right? So that is money. So to answer this question, it's a word problem. We need to give our final answer with units. This one is money for the tickets. It costs $142.50 for the 4 tickets. Okay, so your homework is going to be to do a similar problem. Okay, so make sure you understand this process. First, writing the equation, very similar to what we were doing with writing expressions, except now we set it equal to f of x, right? If we ignore the equals f of x, 35x plus 250 is the same thing we were doing last chapter, where we were given information and we wrote an expression. So this time we're writing our expression equals to f of x. We need to make sure we have a few things when we're writing this. The first thing is we need to define our variables. Notice I defined X as the number of tickets. You're always going to define your input value. So what information did I need to know in order to solve it? I need to know how many tickets there are. So X is the number of tickets. That's number one. We always need to have our variables defined. Number two is we need to set up an equation. So that was part of this question, but even in future questions, if you're ever given a word problem, you need to set up an equation for it. Not just kind of manipulating numbers until it feels right. We're going to set up an equation. That's part of our algebraic learning, is setting up equations. Okay, and then next we need to solve our equation. That's step 3. Sometimes we'll get a number, sometimes it'll just be simplifying the equation as much as we can. And then lastly, we need to write our answer with units in response to the question being asked. Okay, so 4 parts that we always need for a word problem. We need to define our variables. That's the most important one that people forget all the time. Define your variables. Step 2, write an equation. Step 3, solve the equation. And step 4, give your solution with units in answer to the question. Okay, now a lot of teachers will say step 4 is to write a sentence as your solution. I'm not going to require that you write a full sentence, but if your answer is just a number, that is not enough. That will not count. So word problems are worth 4 points. Whenever I give you a word problem, It's worth 4 points. If it's on Math Excel and you get the answer correct, but you don't have those 4 steps, you will get 1 out of 4 points for a correct answer on a word problem. That's not enough to get the correct answer. You have to show me that you know what you're doing and that you know the steps. Okay, so we're gonna start by practicing one for homework. We'll go over it in class tomorrow or next class. That's going to be this question right here. You're buying bottles of a sports drink for a softball team. Each bottle costs $1.19. Each bottle costs $1.19. What function rule models the total cost of a purchase? Evaluate the function for 15 bottles. Notice this is a little bit different than the one that we just had because there's not an extra thing that happens, right? In the last one, it was $35 for a ticket, and also there was an extra fee. This one, it's just water bottles, or a sports drink rather, for a certain price, okay? So it's a little bit different than the last one. It's a little bit easier, but if you don't recognize that difference, it could be a little bit harder, okay? So remember those 4 steps. And then the second part of your homework after you do the word problem is to do our lesson check. Both of these slides are attached to the assignment where you will upload your written work. Upload your written work. And guess what format it should be? That's correct, it should be a PDF. Okay, we still have people forgetting to upload their work. We still have people uploading JPEGs and PNGs. Neither of those is acceptable at this point. We are almost a full month into school. Show all of your work, upload it to Blackbaud as a PDF. One PDF document with the word problem, and then underneath the word problem is the lesson check, all 7 problems, okay? If you have any questions, please feel free to email me and I will get back to you as soon as I can. Remember, my email hours end at 6 p.m. every night.